What would happen if the first moment James Webb opens its eyes to look at the universe, it doesn't produce any clear image at all? The super telescope, worth $10 billion, 20 years of preparation, expected to find traces of life beyond Earth, but the data sent back is only blurry, distorted frames. Not a transmission error, not a misaligned mirror, not a collision in space. An invisible electronic effect sneaking between the pixels is quietly distorting the light that JWST captures at a position 1.5 million kilometers from Earth where no manned spacecraft can access to repair. While the engineering teams are fumbling with a problem that is almost impossible to intervene directly, in a small lab on Earth, two young researchers choose a completely different approach, not touching the hardware, just using a few lines of code and an AI model named AMIGO to untangle the entire data. How can an algorithm overcome the limitations of sensors in space? And from the moment AI begins to intervene in astronomical data, can we still look at the universe in the old way or not? That is the story you're about to watch.
In the cold void, 1.5 million kilometers from Earth, a terrifying truth is unfolding. The first images that James Webb sends back are completely blurry. Not a data compression error, not cosmic wave interference, but a sign that humanity's $10 billion in 20 years of waiting might soon turn to dust. At the Lagrange L2 point, where no astronaut can access for repairs, JWST is drifting in absolute solitude. This is not a satellite that can be pulled back to Earth. This is a suicide mission. Just one tiny detail failing, as thin as 1/10 the thickness of a hair, and the entire super telescope will become scrap floating in space. But before everything collapses, let's rewind a beat to understand why JWST is so important that just one blurry photo is enough to leave all of NASA stunned. James Webb is not just a telescope, it is a machine that looks through time, eyes that can observe stars born over 13 billion years ago, humanity's greatest hope to search for traces of life beyond Earth. Deployed like a golden petal unfolding amid endless darkness, JWST operates with gold-plated mirrors so exquisitely precise that just one small misalignment is enough to destroy all the data. Yet right when its planet-hunting mode is activated, the images sent back are blurry as if someone had jostled it at the decisive moment. What happened? Are we witnessing the moment when humanity loses the chance to see its first cosmic neighbor? This is where everything begins.
At the time NASA began investigating the cause of the blurry photos, they discovered the problem originated from what is considered the life-hunting eyes of James Webb, AMI mode, aperture masking interferometry. This is the technology that allows JWST to see tiny planets hiding in the glaring light of their parent stars, and it operates in a way so strange that it's almost counterintuitive. Instead of opening the entire 6.5-meter primary mirror to collect light, JWST deliberately blocks part of itself. On the mirror is a mask with small holes, creating extremely delicate interfering light rays, like when you raise your hand to shield the sun to see a hazy airplane gliding across the sky. AMI helps JWST block out the overly strong light so that weak and fragile objects like an Earth-like planet emerge from the darkness. But AMI is not just a clever technique, it is the heart of the mission to search for life. Because to know if a planet has life or not, we must see its atmosphere. We must separate the planet's light from the host star's light. We must see signals so small that it's like trying to distinguish a whisper in a storm. And AMI is the tool that helps JWST do that. Without AMI, JWST is like a blindfolded giant, unable to see the small, hot, weak planets close to their parent stars, places where life might exist. Therefore, when the data from AMI is blurry, the scientists immediately understand what that means. The most important part of the entire telescope might be having a problem. This is not just an image error, this is a direct blow to the ambition of searching for biospheres beyond Earth. And if they cannot restore AMI, the hunt for second Earths might end right from the moment it begins.
When NASA began dissecting deeper into the distorted AMI images, all familiar hypotheses were quickly eliminated. The mirrors were not misaligned, the lenses were not vibrating, there was no micrometeoroid impact. All physical traces were completely normal. Yet the data was still distorted in a strange way, subtle, hidden, and particularly dangerous. The interference patterns that should have been sharp as a knife's edge were suddenly stretched, off-axis, blurred in ways no one could explain. And when the AMI mission depends entirely on the purity of each light-dark sample at the sub-pixel level, just a small deviation is enough to completely erase the signals of weak objects lying right next to a bright star. Finally, NASA identified the culprit, charge migration, the phenomenon of charge shifting between pixels of the infrared sensor linked to the brighter, fatter effect. In simple terms, instead of containing charge neatly within each pixel as designed, JWST sensor allows electrons to gradually overflow, swell, and spill over to adjacent pixels. Just a small percentage of charge shifting is enough to break the delicacy of the AMI interference rings. The bright point that should be round and sharp is instead stretched, deviated far from its true position. The interference patterns, which are the backbone of the AMI technique, are blurred, distorted, and asymmetrical just because the charge won't stay still. The most worrying thing is, this error cannot be fixed with hardware. JWST is 1.5 million kilometers from Earth, too far for any astronaut or robot to access. Once JWST unfolds and stabilizes at the L2 point, all physical interventions are impossible. If the sensor has a defect, you only have two choices: live with it or accept that an important part of the mission will forever be limited by it. And charge migration is an inherent error. It's not an unexpected incident, but the nature of the type of modern sensor JWST is using. No software patch can change the physical structure of each pixel. No repeated measurement is enough to separate the shifted charge amount. No classical image processing algorithm is strong enough to recover the interference pattern distorted to the point of being almost unrecognizable. Those problems made the atmosphere in NASA's meetings heavy. No one wanted to say it outright, but everyone understood if they couldn't overcome charge migration, JWST might never achieve the designed AMI contrast. Extremely difficult bright-dark targets like brown dwarfs or planet-sized companions next to parent stars might forever be out of observation range. The theoretical resolution of AMI might only remain on paper. Difficulties piled up. Charge migration is too small to measure but too large to ignore, too complex to model accurately but too systematic not to affect. Like an invisible noise shadow, it sneaks into every pixel and distorts everything JWST tries to see. So how to fix an error that can't be measured, can't be touched, and can't be eliminated by any traditional optical tool? The answer came from an unexpected place, not NASA's control room, not a high-tech center, but from two young researchers in an ordinary lab, those who dared to ask a question the whole industry had never thought of. If we can't fix the sensor, then can we teach AI to understand that error and reverse it itself? And that's when the story of AMIGO begins.
While NASA continuously held meetings to find a solution for the data distortion phenomenon that AMI was facing, in a place thousands of kilometers away, another story began to unfold quietly, without fanfare, but it was about to become a turning point for the entire JWST mission. Louis Destowatz and Max Charles, two young researchers at the University of Sydney, were not part of any NASA advisory board, were not assigned to repair JWST, and didn't even have access to the project's most sensitive data layers. But they had something that science sometimes fails to retain: bold thinking and the recklessness of youth. It all started from something very small: an article about charge migration, the phenomenon of charge shifting between pixels in JWST's infrared sensor. When the light is too strong, the charge doesn't stay put in its pixel, but spills over to the side, causing the brighter, fatter effect, making bright points swell and causing AMI interference patterns to become distorted. Just a few percent of charge drifting astray is enough to collapse all the information that JWST itself is trying to capture. When Louis and Max read this, they posed a question that almost no one in the field dared to ask. If we can't fix the sensor, could we fix the sensor's error with software? To many, this question seemed like something not to be considered, because astronomical data in principle must maintain its integrity. An algorithm that's too powerful could easily draw in bright points that don't exist. A small error from AI could be mistaken for a new object in the universe. And so for decades, the idea of letting AI directly intervene in raw data was always seen as invalid. But Louis and Max didn't want AI to draw anything new. They wanted AI to forget the things that didn't belong to the universe. The excess electrons swelling out, the bright spots being pulled off, the traces that charge migration left behind. If the error has a pattern, AI can learn it,
And if AI learns the pattern of the error, then AI can reverse it. With that thought, they began doing what no one else did, building a miniature version of JWST in the computer. First, they simulated thousands of perfect AMI images, the images JWST should have captured if there were no charge migration. This was the original universe, an ideal version without any distortions. Then they did the opposite, wrote algorithms to destroy those perfect images. Charge migration was simulated with sophisticated physical models. How much charge is pulled to the left? How many percent leaks downward? In which direction the bright point swells when the photon count increases? Every small deviation was recorded, labeled, and fed to the AI to learn. When the AI looked at both versions side by side, the original universe and the universe distorted by charge migration, it gradually learned the signature of the error. It learned to recognize what was distorted, what was real, what was true light, what was the excess that the sensor created. Louis recounted that the moment AMIGO successfully reconstructed the first interference pattern was when they knew they had touched something bigger than they imagined. From a distorted bright spot, AMIGO returned sharp interference rings as if they had never been deviated. Max said, "It was like watching someone clean the glass from the inside rather than from the outside." But to turn the idea into a real tool, they still had to overcome the biggest barrier, the caution of the scientific community. People feared that an AI too powerful would lose the originality of the data. But Louis and Max didn't build AI to imagine new things. They built AI to forget the things that didn't belong to the universe. When they named the system, they chose a name with a human touch. AMIGO, friend. A friend that helps JWST see exactly what it should see. A friend that erases defects that no one can fix by hand. A friend that does what hardware cannot do. When AMIGO completed its test version, they sent it to NASA. They expected nothing. Perhaps the email would be buried in thousands of letters each week. Perhaps no one would pay attention to two young researchers unrelated to the project. But NASA opened the file. NASA ran the test. And NASA saw something no one expected. What happened next would change the future of JWST.
In the days after sending the draft to NASA, Louis and Max barely slept, not because they were waiting for a reply, but because they still couldn't fully believe what they had just created. AMIGO was unlike any astronomical image processing algorithm that had come before. It didn't just sharpen images, reduce noise, or rely on familiar linear filters. AMIGO learned to think like an optical system, not like a post-processing tool. It simulated from the inside. It understood how light passes through the interferometry mask, how diffraction patterns form spirals, how the sensor collects photons, and how charge migration causes bright points to swell. It was learning physics, not pictures. To achieve that, Louis and Max had to build a miniature universe inside the computer, a place where every photon had a documented origin. Every interference fringe had a mathematical source. Every bright point was absolute truth, untouched, undistorted by charge migration. In that simulation, Amy worked perfectly, as if JWST had no hardware flaw at all. That was step one, teaching the AI to see the universe as it truly is. Then they did what seemed to go against all common sense. They deliberately destroyed those perfect images. Using NASA's own charge migration models, they wrote code that made electrons refuse to stay put, gradually flowing into neighboring pixels, causing bright points to swell according to the brighter fatter effect, and dragging interference patterns exactly the way JWST was experiencing in space. A single bright point would be distorted in hundreds of different scenarios. A perfect interference pattern would be turned into warped streaks of light. That was step two, teaching the AI to see the faulty universe, exactly as JWST's sensor produced it. By looking at the universe twice, once pristine, once corrupted, AMIGO began to recognize the unique signature of charge migration. If a bright point swelled 3% along the horizontal axis, the AI knew it was a trace of charge migration. If an interference ring shifted half a pixel downward, the AI knew it wasn't real signal.
And from millions of such observations, AMIGO developed an almost unimaginable ability to return the image to its true optical principles without adding or inventing anything. That was step 3, the real breakthrough. AMIGO gradually became able to take real JWST images and peel away each layer of error, as if wiping dust from an ancient telescope lens. If a bright point was dragged off center, it pulled it back to the true center. If an interference pattern was tilted, it straightened it. If a dark region had been artificially brightened by charge migration, it restored the original darkness. Not with ordinary beautification methods, but with pure physical logic, based on the billions of simulations it had learned from. Lewis later recalled the moment AMIGO successfully restored its first interference pattern from simulated data. In the darkness of the lab, lit only by the faint blue glow of the monitor, from a distorted blob of light, sharp, coherent, breathtakingly beautiful interference rings gradually emerged. They had to look several times to be sure it wasn't an optical illusion. Max said, "It felt like AMIGO was wiping clean a window that we ourselves had deliberately smeared." The most important thing, AMIGO didn't guess. It reconstructed. It restored structures that physics demanded without ever drawing anything extra. That was the crucial difference. Only if the AI never fabricated could NASA dare to insert it into the official analysis pipeline. And somehow AMIGO passed that strict standard. Every pixel was returned exactly where it would have been if JWST had been free of charge migration. The boldness of Lewis and Max, once just a "let's give it a try" idea on a restless evening, had become a tool with the potential to transform an entire branch of astronomical observation. But all of this had only happened in simulation so far. NASA had not yet tested it on real data, and when the reply email finally appeared, the very first line was enough to tell them everything was about to change. "You will want to see this." AMIGO was about to face the real universe, and what happened next could rewrite the limits of the telescope.
When NASA finally agreed to test AMIGO on real JWST data, the control room fell so silent you could hear pens tapping on the table. No one said it out loud, but everyone knew either AMIGO would become a revolution or it would simply join the long list of ideas that were nice but not good enough for the universe. For the test, NASA selected the targets that Amy had already photographed but failed at, images so distorted, so blurred, they were practically useless. If AMIGO could handle the very worst cases, they would have to take it seriously. The first image fed into the algorithm was of the star system HD 206893. In the raw frame, the central star blazed so brightly that everything around it was smeared into a blur. The companion object, a faint brown dwarf, was completely lost in the elongated noise streak caused by charge migration, the shifting of charge between pixels that triggers the brighter fatter effect. To the human eye, it was just a deformed bright spot. To ordinary software, it was a chaotic jumble of signals. But to AMIGO, this was the chance to prove it understood JWST better than JWST understood itself. As the algorithm ran, layer after layer of error was peeled away in a way no human eye could achieve. Pixels dragged to the left, AMIGO pushed them back. Interference fringes shifted half a pixel, AMIGO aligned them perfectly. Bright regions bloated by charge migration, AMIGO neatly pulled them back in. Each tiny correction built up like watching someone wipe a wet cloth across a dust-covered mirror. And then, the moment that silenced the entire room happened. Two light sources that had been fused together in the original image separated cleanly, like two diamonds against a black velvet sky. The blazing host star, and right beside it, a faint but razor-sharp object, the brown dwarf HD 206893b, appearing for the first time in the exact shape physics demanded. An older engineer leaned forward, squinting at the screen as if he couldn't believe this came from real data. Someone else exhaled softly. "This has never happened before."
But NASA didn't rush to judgment. One example wasn't enough. They fed AMIGO one of Amy's toughest targets, WR-137, a Wolf-Rayet system with dust plumes erupting like cosmic tornadoes. Although JWST had captured plenty of detail in regular infrared, the AMI images of WR-137 were nearly meaningless, everything stretched, twisted, and buried under charge migration noise. AMIGO took the data like a master jeweler restoring a dirt-encrusted antique. At first, the screen showed only scattered streaks of light, but the longer it ran, the more the spiral structures predicted by theory years ago began to emerge, drawn in silver ink against the darkness. Dust rings swirling around the Wolf-Rayet star, layered, folded, terrifyingly beautiful. These were structures no telescope had ever seen clearly before, and they appeared not because of better hardware, but because of an algorithm written in a small lab in Sydney. Researchers stood up from their chairs. Some burst out laughing from sheer relief. Others just stared at the screen trying to burn the moment into memory. NASA's internal report concluded, AMIGO restores data to the maximum sharpness allowed by the diffraction limit of physical optics. That is the highest praise any astronomical data processing algorithm can receive. In just a few minutes, AMIGO erased months of dread. It added nothing to the universe. It only removed what didn't belong there. For the first time, JWST could see what it was always meant to see, if it had not been born with that congenital flaw. And in that moment, NASA realized they hadn't just fixed a bug, but had opened an entirely new door in how humanity builds telescopes. The next part will go even further, not just fixing errors, but asking whether we still need perfect telescopes at all, or whether the era of soft telescopes, where software surpasses hardware, has already begun.
When NASA finally confirmed that AMIGO had restored the data all the way back to the physical diffraction limit, something strange happened. For decades, astronomy had treated the telescope itself as the thing that must be perfected first, physically, mechanically, obsessively, while the data was merely collected passively. For the first time, that hierarchy began to wobble. No one said it out loud, but in every email, every meeting, every whispered hallway conversation at Goddard Space Flight Center, a small but heavy question started to sprout. If AI can save a $10 billion telescope from a hardware flaw, do we still need telescopes that are obsessively perfect? That question wasn't just technical, it was a direct challenge to a decades-old article of faith in the field. Until now, every telescope from Kepler to Spitzer to JWST had to achieve absolute precision. A mere misalignment of a few tens of nanometers was enough to halt a project, but AMIGO demonstrated the opposite. A telescope doesn't have to be perfect as long as its imperfections are learnable. A sufficiently good artificial intelligence can strip away most complex optical and electronic errors. So what happens if we dare to dethrone hardware from its secret pedestal of perfection? The first hypothesis emerged quickly. The future might belong to cheaper, lighter, less finicky telescopes, mirrors that don't need to be polished to the ultimate limit, sensors that don't have to be absolutely noise-free, systems that can tolerate 20 to 30% deviations. Instead of spending billions of dollars chasing perfection, we let software clean up afterwards. This isn't damage control, it's a completely new design philosophy, the soft telescope, where software is so powerful that it changes the very way we look at the universe. Many people started sketching bold visions. Instead of one JWST that took 20 years and $10 billion, we could have 5 JWST-class instruments for $1 to $2 billion each, scattered at different points in the solar system. An idea once dismissed as fantasy suddenly felt strangely reasonable with AMIGO in the picture. Some scientists even whispered that if AI can correct optical errors like AMIGO does, we might someday use mirrors that are slightly warped, slightly misaligned, or so light that traditional precision is impossible as long as we can simulate exactly how they fail. But it's not just about cost. The second hypothesis is even bolder. If an algorithm like AMIGO can push contrast all the way to the physical limit, objects that were previously invisible, for example a rocky Earth-sized planet hugging its parent star, could become detectable. Until now, we've only found super-Earths and gas giants because they're bigger and brighter. But life might be hiding on small, dark worlds drowned in stellar glare.
What AMIGO did for HD 20689b and WR137 is only the beginning. If the algorithm keeps evolving, it could peel away signals so faint they sit right on the quantum noise boundary, where humans once believed nothing but chaos could be seen. Of course, alongside the dream comes a very real fear. What if one day the AI becomes so powerful that it reconstructs more than it restores? The fear that a tiny bright spot differing by just 1% from the model will be wrongly interpreted as a planet. The fear that high-frequency noise will be mistaken for an atmospheric signature. The fear that a random dust spiral will be upgraded by AI into a cosmic structure that never existed. That fear is not irrational. AI is famous for its ability to hallucinate. And so the great debate erupted. Where is the line between real data and reconstructed data? When the difference between the two is measured in a handful of stray electrons, humanity is forced to confront the fact that our very knowledge of the universe may now depend on an algorithm. Astronomy stands at a crossroads right now. On one side lies the tradition of physical perfection, on the other, a new philosophy. The universe can be unlocked by software. And in the middle is the question that silences every scientist. When AI lets us see things we have never seen before, is that discovery or illusion? There is no simple answer, but as AMIGO continues to prove its power, one thing becomes clear. This revolution has already begun, and there is no going back. The final part will be the conclusion, where hardware and software merge, and the future of cosmic exploration is rewritten.
When the final images processed by AMIGO appeared sharp to the point of seeming unreal, both NASA and the astronomical community were forced to accept one thing. The journey of exploring the universe from here on would no longer be the same. JWST, the brainchild worth $10 billion nurtured by 2 decades of expectations, had been saved not by a massive army of engineers, but by 2 young researchers and a few bold lines of code. The hardware had done the most wonderful thing it could do, but it was the software that unlocked the rest of the universe. In the silent darkness at L2, where JWST is more isolated than any artificial object humanity has ever created, it now has a true companion, AMIGO, an intelligence not housed in the spacecraft, not launched into space, but one that sees things the telescope cannot see on its own, as if we had just given JWST a second pair of eyes not limited by physics. And then, a simple yet profoundly trembling question arose. If tomorrow we discover an Earth-like planet, whose eyes will be the first to see it, JWST's or AMIGO's? That thought made the entire field of astronomy pause for a beat, because the future of cosmic exploration might no longer be a race for larger mirrors, better sensors, or more powerful rockets. The future might lie in something far more intangible, algorithms, not to replace the truth, but to liberate the truth from the hazy noise that devices leave behind. In the end, looking back at this journey from the tiny charge migration era like a speck of electronic dust to the breakthrough that changed the mindset of telescope design, we realize that the universe is not only vaster than we imagined, but also more complex, and that very complexity forces us to evolve, from gigantic gold mirrors to neural networks that read the universe like a native language. So before this video ends, I want to ask you one thing, a question that seems simple but might echo for many years to come. Do you trust universe images processed by AI? What do you think is the boundary between restoration and imagination? Will the future of astronomy belong to hardware or software? Leave a comment below because who knows, your perspective might be the next piece in the story of how humanity sees the universe.
If you enjoy scientific stories told in a cinematic way like this, please hit like so we know you want to see more. And if you want to continue exploring the greatest mysteries of the universe with me, from observation technology to the question of whether we are alone in this cosmos, please subscribe and turn on the notification bell so you don't miss the next episode. Thank you for watching until the end of the video, and see you again in the upcoming episodes.